going to record it to the cloud. All right. So I have a couple of quick announcements for you before we begin today. Quick pop quiz. Where will you be on Friday? Not here. Okay, not here. I have the HLC, it will be the last day of the HLC General Education Workshop. And because of that, I will be recording a session probably tomorrow. It'll be about 30 minutes on sensation and perception. Couple of other quick announcements for you. I hope you enjoyed getting a Friday off, because if I'm not mistaken, you get another Friday off, I think the following week because of mid-semester break. So if it turns out that there's stuff that we're running out of time to cover, I'm probably going to record a video for you to watch on your own time just to make sure we don't lose speed. The other thing that I will mention, we have a quiz that we'll post on Friday, and that will be available Friday at 12 a.m. and it will be due on the following Monday at 5 o'clock. Did you have a question, Bronwyn?
Yeah, is it on chapter 5?
It's going to be sensation and perception only.
Okay.
So you should be totally fine. And for those of you that haven't started reading the book yet, it'll force you to read the book. We like that. We love us a reading quiz that will help you read. Okay, so let's go ahead and share the screen. I promised that today we would be talking about more fun things related to sensation and perception than gross things like eyeballs, and I meant it. I don't actually think eyeballs are gross, but I do have to say, when I first got contact lenses, it took me 15 minutes to put one in. My poor, poor eyes. You have to learn how to fight that blinking reflex. And now I can do it really well. Okay. Okay, so the last time we were here, we finished on the basic idea that you have 3 different types of cones in your retina. So these 3 different types of cones enable you to see any possible color on Earth. Now, let's be really clear, and I got a couple of really good questions about this after class. Everybody loves to ask about color vision. One of the first things that I can tell you is that yes, if you are missing one of these cones, or if one of these cones does not produce the appropriate photopigment, you will have color deficiencies. Additionally, some animals can actually see more colors and more on the electromagnetic spectrum than you can. So there are certain species of, I don't know about shrimp, but I do know that birds can see certain types of ultraviolet light, and then also certain types of species of honeybees and butterflies. Contrary to what you may believe, your cats and dogs do not actually see in black and white. They can actually see color, but they have a reduced color spectrum compared to you. Visible light, just so we're clear, makes up a snippet of what is actually out there in the world. So there are microwaves floating on around us. Okay, so that's a shrimp with different colors, but I don't know if that translates to.
Shrimp, they say it can see 16 colors.
I will look that up, because I don't, 16 color, I mean, we can see more than 16.
No, I mean like, but I mean like.
Mm-hmm. Oh, 16 different types of cones or something like that?
I think so, I don't know.
Mm-hmm. Chelsea.
12 to 16 photoreceptors.
Wow, 12 to 16 photoreceptors. I feel so insignificant with my sad little 3. Now occasionally, you will get somebody that has 4 types of cones. These are what are called tetrachromats. They can actually see finer distinctions between color than you can, but most of us have 3. So when these are maximally activated, you get the color white. Now I know what you're thinking, Dr. Gilchrist, when I mix red, green, and blue paint, or red, green, and blue crayons. What kind of color do you get? I call it nasty brown. It's like this weird gray, green brown. Brown is a beautiful color. Like, if I didn't think brown was a beautiful color, I would have changed my eyes a long time ago, but I love brown. I do not love the brown that is produced when you play with the pigments and you mix all of the colors together. Like, there's just too much gray and brown mixing. I like gray, I like brown. I do not like them together like that. But that's because you're playing with pigment. When you play with light, mixing all of these together will actually produce the sensation of white. And you should not do this. Like, I'm going to tell you, you can do this, but don't look at this too long. If you want to kind of see red, green, and blue light creating white in action, if you stick your face really close to a white screen, you can actually see the separate little pixels of red, green, and blue sometimes. It's probably not going to work with today's monitors, but if you have like an old school TV, like one of those cathode ray tube TVs, you can actually see this. It might explain why my eyes are so bad. Somebody spent too long staring at the pixels in her TV. Okay, so something that kind of fits with the trichromatic theory is color deficient vision. So one of the things that we find is that in general, most people, if they have color deficiencies, have trouble distinguishing between red and green. So can somebody tell me what they see in this bubble? What number do you see? 74. Okay, 74. How about here? 45. These are what are known as Ishihara tests. Ishihara tests are these they're kind of oversimplified, these very simple tests to look at color deficiencies. So color blindness often happens because of genetic factors or congenital issues. And people are either going to be blind to red or green colors. So instead of seeing a distinctive red or green, you're probably going to see something that kind of looks like that weird muddled brown color that I mentioned. It's going to look like a weird gray brown. Most people, if they have color deficiencies, typically, so here's what we know. It's carried on, the gene for red-green color blindness is carried on the X chromosome. If you have an X and a Y chromosome, if you carry the gene on your X chromosome, and this is a recessive trait, if you carry a Y chromosome, there is nothing on that chromosome that is going to be able to cancel out that recessive trait because the Y chromosome does not really carry a lot of genes on it. It's small. On the other hand, because this color blindness is a recessive trait, most people that have at least one more X chromosome will have the dominant allele that will cancel that out. So one of the things that we do find is that for the most part, red-green color blindness tends to occur in people who are assigned male at birth. Not saying it doesn't happen for people who are assigned female at birth. It does happen, but it is significantly rarer because it is an X chromosome linked disorder. Now, something that is a little less common is this would be a case of what the world would look like. One that is less common would be something like blue-yellow color blindness. So this is what the world would kind of look like if you had red-green color blindness. And red-green color blindness can happen in a variety of different ways. It can occur because you don't have a red cone. It could occur because you don't have a green cone, or you could have a problem with the photopigment in either a red cone or a green cone. So it can happen in a variety of different ways. Blue-yellow is less common, but it can happen. And occasionally we get people who only have one type of cone, or people that only have rods. People that only have one type of cone or only have rods do not see color at all. You need more than one cone to distinguish between all of the different colors on Earth. So you need at least two to see color. If you only have one, you are going to see in black and white. And for those who are curious why that is, I teach sensation and perception. I'm obviously going to be on sabbatical next semester, but if you'd like to learn more about color vision and some of the deficiencies, I will be teaching it next spring. Okay, so we're going to try something cool. I want you to stare at this flag, at the center of this flag for as long as you can. And eventually it will disappear to white. And I want you to tell me what you see. Try not to blink if you can possibly avoid it. That's how the weeping angels get you. But that's not why I want you to not blink. What do we see? British flag. Okay, so let's go back really quick. So I know it's not going to be perfect, but what color did the green turn into? Kind of turned into a pinkish red, right? Black turned into white and yellow turned into blue, or a bluish color. Is that kind of what you saw? Okay, do we want to try this for a longer period of time and see if it works? We can. Okay, so I'm going to keep this up for probably about 40 seconds. Try to stare at it for as long as you can. Do your best to try not to blink. Got it now? Okay, so that produced a stronger effect. So the longer that you look at it, the more that you get those different colors. This is what is referred to as a negative after image. So a negative after image is basically when we get those opposing colors after we've looked at something for a really long time. And they can be a lot of fun. So this actually supports something that is referred to as opponent process theory. So what happens when you stare at something for a really long time is that you have these three different opponent processes. So we have red versus green, blue versus yellow, and black versus white. And again, for those who are curious as to how this happens, I can give you a more technical discussion of this after class. But basically, the idea is that when you look at a given color for too long, your cones get tired and the opponent process kicks in. So if you look at red too long, it's gonna make green. If you look at green too long, it's gonna make red. If you look at blue too long, it's going to make yellow. So this fits relatively well with trichromacy. Yes?
Is that how people make those like weird Jesus images when you're like supposed to stare at it and then you look at something white and it turns into Jesus?
Yeah, no, that's exactly how that works. That's a negative after image. So as you're kind of writing this down, I am going to kind of share something embarrassing. I tend to do this a lot with sensation and perception because apparently I was just a really curious kid. One of my favorite things to do when I was in 5th grade, and again, I wonder why my eyes are so bad. And I don't want to say it was my favorite thing to do. My favorite thing was either riding my bike, reading a book, or hanging out with my friends. But one thing that I liked to do was stare at a light bulb until I got the negative after image. And again, I wonder why my eyes are so bad. Could it be that I was trying to do all of this sensation and perception stuff without knowing the consequences? Probably. But yeah, I think it can be said I was a weird child. Staring at light bulbs to get the after image is kind of a weird thing, and I'll admit it. Okay, is everybody good here? All right. Okay, so this one's gonna make you sick, so don't look at it too long. So if you move your eyes around, you can actually see the dots in the middle of the grid shift from black to white or gray to white. Okay, do you want me to turn this off now? Some of you, it might make you feel funny. Okay, this one is my favorite. This one is called vanishing fluff. So what I'd like you to do is try to stare at that black dot, try not to blink, and what you will eventually see is that all that fluffy stuff is going to disappear and leave you with gray. Or leave you with a little less gray. Did it work for anybody else? Okay, you don't need to write this down, but I'm going to show you how this works. Okay, so as you're staring at the black dot and your eye is moving, and folks, your eyes are always moving, your brain stores the visual image of what you just saw. And your brain is going to do that in general because your visual system is looking for change. The opponent process comes in, and with that stored image that you still kind of have lingering, it's going to cancel out the color so that all you see is the gray. So if you see yellow fluff, it's going to store the image of that. The blue after image is going to kick in, and the yellow and the blue are going to cancel out, leaving you with gray. Isn't that weird? I love it. I love weird things. Okay, so now we're going to talk a little bit. So we've talked about our visual sensation and how color perception happens. Now we're going to talk about how we interpret what we see. Remember, I told you we're going to spend a lot of time on vision. So probably on Friday, we are going to finish up vision in that video that I record. And then we're going to talk about hearing and taste and touch. Ideally, by Monday, I would like to start talking about learning and conditioning. Not conditioning your hair. Why was Pavlov's hair so soft, y'all? He used classical conditioner or conditioning. I've got a bunch of dad jokes. My father sends them to me all the time. Also, I heard that the international trip for when many of y'all first years are eligible to go is Vienna. I might have been thinking about planning a module to go see the Freud Museum, because there's a Sigmund Freud Museum in Vienna. I heard there's a good neuroanatomy section. I think I might want to go. I know a little German. I could do it. Okay, so can anybody tell me what they see here? How many of you see one thing? How many? Raise your hand if you see just one thing. Raise your hand if you see more than one thing here. Great. What do we see? What do we see? Michelle?
There's a lady, but also a guy playing the tuba.
Well, that's more of a saxophone than a tuba. And believe me, I would know. I play tuba. It kind of looks, y'all see in The Little Mermaid? It kind of looks like a snarfblat. It kind of looks like a snarfblat. But it kind of looks like a saxophone. Is anybody having trouble seeing the woman's face? If you can't see the face, here's an eye. Here's the bridge of the nose. Here's a lip. Here's hair. Do you have it now? Okay. Now, is anybody having trouble with the man playing the saxophone? Here's his nose. It's quite big. Here's the top of the saxophone. Here's his chin. And then he's going to play that. Do you see it now? Okay. So you can't see both of those things at the same time. You are constantly shifting back and forth between the two. So it's kind of like that one where it looks like a duck, but it also looks like a bunny. I like to call it the dunny. Okay. So when we're looking at visual perception, we have to talk a little bit about we have to talk a little bit about the work of the Gestalt psychologists. So Hey, here's a quick review of one of your short answer questions. So when we talked about the early history of psychology, I mentioned that we kind of started by talking about mental processes. Then we moved, at least in the United States, to a very rigid form of behaviorism where mental states were not considered. And I mentioned that that was primarily a United States phenomenon. Over in Europe, the Gestalt psychologists were still looking at mental states. They looked at things like visual perception and problem solving. Now, the reason that they called it the Gestalt is because when we are visually interpreting our world, we have a tendency to integrate pieces of information into meaningful wholes. Literally, the whole is more than the sum of its parts. And we're using a lot of top-down processing. So using our expectations and our memory and our knowledge to help us navigate our world and interpret what we see. So for example, what does everybody see here? You see a cube. Now, is that cube actually there? It's made up of a bunch of negative space. What you're actually really looking at are a bunch of little pieces of circles, but they're organized in such a way that all that negative space makes you see a cube that is not actually there. So the whole is more than the sum of its parts. Yes?
I feel like the way they made that though was by putting a cube on top of some circles and then erasing the cube.
Well, of course, but it's
So
still
was
negative
there?
space.
Was there?
It's true, but it is still negative space. For example, this is not actually a C. There are missing pieces here. There is empty space on the C of my coffee cup. If you have a coffee logo that looks like this, it doesn't actually close off, but your brain fills in the missing information to create a C. And to be fair, most of the parts of the C are there. So you're just going to fill in what's missing. Okay, does anybody need some more time here? Okay. So one of the ways that the Gestaltists said that we start interpreting the world and recognizing objects around us is by separating an object from its background. So this is the very beginning of how we start to see the objects around us. And so what we do is we basically organize the visual field into objects that stand out from the background. Now, if I were in a laboratory asking you to separate objects from their background, this is going to be a really easy task to do because you've been doing it for years. So oftentimes, if you go into a lab and you're being asked to separate objects from their background, they're not going to ask you to look at everyday objects. They're going to make you look at something like this, where you are constantly reversing the object from the background. So what do you see when you look at this figure? Can somebody tell me what they see?
You mean like initially,
Yeah, what do you initially see in that figure?
bunch of people like going downstairs?
People walking downstairs. Does anybody see anything different? Yeah, Chelsea.
Arrows going that way. They're diagonal.
Right. So we can see arrows, so white arrows against a black background, or men in black going against a white background. So we are constantly, once again, shifting back and forth between these two images. So for example, whatever is the figure or the object standing out from the background will have form and obvious shape. So when we're focusing on the men going down the stairs, we don't really see the arrows. They're just a white formless background. Once we shift to the arrows as the figure, the men are no longer visible. We instead will see a formless formless black background. Ribs. They said ribs on there. Now I've got that goofy Chili's baby back rib song in my head. I got my baby back ribs.
I'm a baby bear, baby bear, baby back ribs.
I do have to say, when the transcription comes out, when it's completed, it's much better than the real-time one. Like in general, I don't see this kind of stuff when I'm entering in captions. It's mostly just, most of the time, punctuation or failure to enunciate on my part because I talk too fast. But we already knew that.
I totally know what you mean. I have a alarm that uses like a Siri, and you have to turn it off by saying, "Hey Siri, stop." And every morning it takes like 10 tries before it can hear me.
Yeah, we haven't really done a very good job with like AI being able to decode speech signals. It's one of the harder things that we still have to work on. Okay, so here is another example of a reversible figure and ground. I thought I would share this with you because frankly, these are fun to look at. So here you can see gray swans against a white background or white swans against a gray background. Okay, so once you have actually separated an object from its background, you have to start figuring out where the edge of one object ends and another begins. So you've got to start separating objects from each other. One of the ways that you can do this is through what the Gestaltists called grouping principles. So we tend to organize visual stimuli into different groups. And again, because these are the Gestaltists, they are going to say that the perceived whole will actually differ from the individual sum of its parts. Everybody good, or does anybody need some more time? Cool, thanks.
I still think it's so funny. It's like baby bear.
I was gonna say, I think you might have missed the day when we had the auto captioning for one of the videos. And I think I don't use this word lightly, but I think I might have been a little traumatized by that, by the auto caption. I was like, no, I don't need to see that word. And that was definitely not the word. If
What
you
did it say?
have one of the students talk to you after class, I will not do it here, for I am too prudish. It was, it referred, yes, it referred to anatomy, and that is all I'm going to say. And the other hint is that it was based on Christmas tree. Okay, and that's all I'm gonna say. Okay, are we good now?
Yeah.
I so want to move on. I want to move on to the next slide. Can I do that, please? Okay, thank you. Okay, so here are some of the different grouping principles. So I'm going to spend a little bit of time on this slide just to kind of show you in each of these cases how the whole differs from the sum of its parts. So the first grouping principle is the principle or the law of proximity. So you can either call this the principle of proximity or the law of proximity or the rule of proximity. The idea here is that objects that are closer together are more likely to be grouped together. So for example, Haley and Tracy like to sit together a lot, and so I'm going to tend to form them in my mind as a group. In this example, we have 6 different lines that are present. Because of the rule of proximity, I'm going to be more likely to group these 2 lines together than these 2, because these 2 are closer together. So I actually have the perception of 3 thick vertical stripes instead of 6 separate lines. Now, everybody is a little bit different when it comes to these grouping principles. So if you do not see the 3 thick vertical stripes, that is okay. Everybody is a little bit different with these. And we do actually find that some of these grouping principles vary across cultures as well. Next, we have the rule of similarity. So right now I am looking at a triangle, a circle, and a triangle. Now, how many of you are organizing those by row? So we have a row of triangle, circle, triangle. How many of you are organizing them in columns? So you're going vertically. Odds are pretty good more of you are going to do that vertically than horizontally. And that's because similar items are going to be grouped together. So I'm going to be more likely to perceive this as a vertical group of 3, another vertical group of 3, and another vertical group of 3. Next, we have the rule of continuity. It is also sometimes called the rule of good continuation. So one of the nice things about being on Zoom is that I can annotate, but I think Zoom froze up, so it won't let me. So you're just going to have to follow my cursor here. So if you're like me, what you're perceiving right now is this wavy line cutting through a straight line. Now, you thought it was semicircles?
No, those sine waves.
Yeah, it does kind of look like a sine wave. So the Gestaltists believe that when we see something like this, we're not going to perceive something like it starts going up and then it turns back and then it suddenly makes a semicircle and then it goes straight and then it makes this one. We perceive lines as moving smoothly and continuing on in that same direction. We don't make sudden changes or sudden switchbacks or sudden shifts. And then finally, we have the rule of connectedness. Does everybody else see barbells or dumbbells? Or maybe glasses? They look like a lot of different things. The idea here is that items that are connected, even by a simple line, are going to be grouped together. So instead of perceiving 6 separate circles, go back. Instead of perceiving 6 separate circles, we see 3 dumbbells or 3 sunglasses or whatever else you see them as. Oh, that's fine. I'm not going anywhere until y'all say you're ready. Okay. All right. So another example of this is the rule of closure. So much like we saw with the cube earlier, what do you see here? You see a triangle. Do you see that triangle here? No. The triangle, there's not really a triangle here, but when we have this negative space, we perceive a triangle. Now, here's my question to you. If I removed this triangle, what would I expect to see underneath? Would we expect there to be circles? So the idea here is that we have a triangle, I'm going to trace it for you, that is basically in front of 3 sets of circles. The reason that you don't perceive that anymore is because I've basically cut off what you think are circles, and now they're all C's. So now you no longer see the triangle in negative space. So closure is when we close off negative space in a figure, even if there are no lines to actually do so. Okay, everybody good? All right. So here's a case of Gestalt principles at work. So here we have somebody building a house for the cute cuddly puppies. Watch this. That's not actually what the house looks like. There's actually a lot of negative space there that is basically filled in by the puppies. So it looks like a fully built house with puppies running around it. But when you actually look at it, there are a lot of gaps that are missing. But because of the way that we use closure to cut off figures, we perceive that there's a straight line underneath this puppy, or that there's no gap right here. So we're basically closing off all of that negative space. When the puppies aren't present, all of a sudden we have trouble doing that. Okay, so now we're going to kind of move on to talking about depth perception. So once we have identified an object, we've removed it, we've been able to separate it from its background, we need to figure out how far away it is from us. So depth perception is kind of critical. You are constantly interacting with objects. And I know what you're thinking, Dr. Gilchrist, I'm not interacting with any objects. Oh, yes, you are. You're all typing on computers, reaching for water bottles, grabbing pens, checking phones, all of that stuff. For you to be able to do any of that, you need to have accurate depth perception. Otherwise, you're constantly missing what you're trying to reach for. And you're probably walking into things, and that's no good. So one of the things that we know is that depth perception actually develops relatively early in children. So one of the things you'll kind of see now, one of the ways that researchers have tested this is with something called the visual cliff. So one of the things that we find, we can set up this scenario. Oh, the chair was trapped. Ow. I hit my funny bone of my knee. I hit my kneecap and it feels weird. Okay, I'm all right. So we have this scenario where we basically have a plexiglass table. Now, I want to be really clear here that this infant is supported at all times, but the table has been decorated in such a way that it looks like there is a sudden sharp drop off. And so at least initially, if a parent stands on the other side of this table and tries to get their child to crawl over to them, they will not do it. But what's kind of interesting is that they only learn this ability right around the time that they actually start learning to crawl and walk, and they realize that falling hurts. So once we realize that falling hurts, all of a sudden we're able to perceive this sudden drop off. Prior to learning that falling hurts, animals and also infants will have no trouble crossing this cliff. But once they're a little older and they've developed that depth perception, they will not do it. So I actually saw a really interesting TikTok on, I think it was on Twitter, of a child, maybe about 2 years old, definitely capable of walking. And there was kind of this, not suspended bridge, but it was like a clear glass bridge. So you could see all the way down, totally strong, totally supported. But what was interesting is that the kid was on 2 feet, and to get over onto that bridge where you can see straight down, he started kind of getting on his knees and kind of staying really, really close to the edge. So once we realize that falling hurts, we're very suddenly not going to take a sudden drop off. And the researchers have tried this with different animals to get some very interesting results. But depth perception is important. It makes sure that you can navigate the world around you, and it helps you figure out how far away you are in relation to objects. It also helps you see in 3 dimensions because you live in a 3-dimensional world. So depth perception helps us for a couple of different things. First of all, it helps us see in 3 dimensions. Additionally, it helps us judge distance from objects. And there are different types of cues that we can use to help judge the depth and distance of things. So we have cues that use both eyes, and we have cues that use a single eye. So the ones that use both eyes are what are called binocular cues. So we call them binocular because it's 2 eyes. So ocular here means eyes. So once you're done writing this down, I want you to try something. So I want you to take one finger, put it right in front of you, maybe just like this. Then I want you to take your other finger and I want you to stretch it all the way out at arm's length. And what I'd like you to do is open one eye and then the other. And what you should perceive is that the finger that is closer to you is jumping back and forth across the finger that is farther away. So here's something kind of interesting. Your eyes are not on top of each other. I know, what a revolutionary idea. Each of your eyes is occupying a slightly different position in your head, and as a result, it's getting a slightly different view of the world. And it's that difference in the viewpoints and the perspectives between our 2 eyes that allow us to see depth and distance. So you noticed that your finger that was far away appeared to jump back and forth over the finger that was farther away. So one of the things that we know is that this difference between our 2 eyes is bigger for objects that are close to us compared to objects that are farther away. So if you do this again, and instead focus on the finger that's far away, instead of the finger that's close to you, that far away finger shouldn't appear to jump at all. And that's because the disparity is less noticeable for objects that are far away from us. It's more noticeable when objects are close to us. And we can actually use that disparity to figure out where objects are. If you go to 3D movies, they actually exaggerate the disparity between your eyes to get a 3-dimensional image on the screen. You have to wear those special glasses. They help kind of correct that disparity and give you that sense of depth. And then one of the other things that we use to help us with depth is what is called convergence. So if I'm reading, I'm going to notice that my eyes, if you were taking a picture of me reading something close up, you're going to notice that my eyes are going to turn inward towards each other. For objects that are farther away, they are not going to turn inward. So generally for objects that are closer to us, we basically will roll our eyes in towards each other to help us focus. This can also help us with depth and distance. So now we have to talk about the monocular cues. These are cues that we only need one eye for, but I want to show you this first. So I think I'm going to go ahead and stop here for the lecturing, and I'm going to show you a video of the mysterious floating cube, and then I'm going to show you a T-Rex. And that's how we'll end class today. So we'll talk about the monocular cues, and I will finish up vision on, Okay, so I'm going to go ahead and end here and then we'll watch that video.